All right, so welcome to an example where we apply our understanding in the disk method into finding the volume of a solid that is generated by rotating a region around a given axis. Okay, and so to move on any further on this example right here, I highly recommend this lesson, this example is to be viewed after you have viewed my lecture on the general discussion about the disk method, or the general discussion about the how to find volume using calculus, how to find volume of a solid that is generated by rotating a region around a given axis. Okay, so here we go. Let's dive into the problem here, and let's get started by looking at the wording description, or the worded description of our problem here. Okay, so now on my computer screen here, I have prepared the following problem. Okay, so we want to find the volume of a right circular cone with height 6. So the characteristic of this is the characteristic of what that solid is. It's a right circular cone, and with height 6. Okay, with height 6, and with base radius 2. Okay, base radius 2. All right, so the problem looks surprisingly simple, and the point now of this problem is that we must use our calculus understanding into solving this problem, because as a matter of fact, now let's go ahead and have a quick sketch of the problem right here. So first of all, it's a right circular cone. So anyone viewing this video lesson is not surprised at all about what a right circular cone is. In case you're not aware, then a right circular cone is just something like this. You see these kind of things for workers who work on the street a lot. They use this to, block traffic, right? And so it's a right circular cone in the sense that it's standing up. Once you're standing, it stand up straight from the ground right here. So that height right here is what's indicated for us according to the problem. This height, okay, that's the height right here, and that height right there is 6. And we can disregard about units right here. It could be 6 centimeters or 6 feet or 6 whatever, okay, or 6 inches. And then the base radius as indicated in the problem. So here's base radius being 2, okay, because the idea of a right circular cone is that, well, it's round. That's why it's called circular, because the base here has to be a circle shape like this, and it's standing upright, standing straight up. So the height here is here, I explained. And so the base radius is from where that height dropped down to the bottom part of the cone right here. Then that base circle has radius 2. That's what it means by the base radius. Okay, so R equals 2 in that. Okay, so that means the base of this circular cone here, of this right circular cone, the base has diameter 4. Okay, but having diameter or not is, knowing about the diameter or not is just optional. So right now, as a direct given information, then we're looking at the height here being 6, and the radius equals 2. The base radius equals 2. Okay, now for anyone who just got out of high school geometry, this problem is completely within your reach. Okay, because the volume of any right circular cone like this one right here, once we have the base radius, is simply the volume is 1/3 times r squared times height right here, and we have all that information. This is the height is 6, the radius here is 2. So, and I'm lying a little bit, pi r squared. Sorry for my little mistake. Okay, so 1/3 pi r squared times h. Okay, and so that is going to be 1/3 pi times 2 squared times 6 right here. So all together, I am expecting, so I know that the volume here is and the 6 here cancel with that 3 here and leaves behind a 2 here. So all together is going to be an 8 pi. That's the volume of this. Okay, so as I'm saying, we have a quick way to know the answer. High school geometry students know this answer right here because we have a formula. But the point now is that this problem, we want to see how we can use calculus. So this problem here, admittedly, is a problem where it takes it takes your creativity to the next level right here. We want to, so we don't want to use that formula where, you know, the high school geometry students are doing. We want to use calculus, and in a sense that we're gonna, from this problem right here, from the way how we approach using calculus right here, we are going to be able to see more about where this formula kind of came from. Okay. All right. So now let me erase that solution. So we kind of know that the answer has to be an 8 pi. Okay. But let's find out how. So I drew the picture, but I completely erased that because. So here's the idea. So using calculus, and at this point, and as I have said in the beginning of this video lesson here, then we are going to use specifically the disk method. We are treating the idea now is that, and I brought up this problem as an example so that I want you to realize how many solids out there in your daily life come out as a product, as a consequence of rotating a region around a given axis. And the cone we're about to do here is one. Okay, so how about let me demonstrate that in a graphical picture over here. And by the way, a cone, yes, it's called a right circular cone standing straight up. The more precise meaning is that the height is perpendicular with the base right here. That's why it's called right circular cone right here. But as far as the orientation, you can seat it straight up like this, or you can also put it sideways. Okay, it's still a right circular cone. The base is here, that's base radius, and that's the height right there. Now it's sitting sideways. Okay, so that's another detail I just want to mention right here. You can seat your circular cone standing straight up, or you can kind of put it sideways like this. Okay, and then I'm now going to start pointing out for you how this volume here, this solid here really came out from as a result of rotating a region. Okay, so now allow me to switch over to the computer screen right here. And I'm going to use Desmos again to do that demonstration. All right, so here we go with Desmos here on my browser. And with Desmos.com, here's just the cone, just some cone. Now, it's not necessarily that we have height 6 or base radius 2. That's not the important point. But now, in this cone, I'm putting it sideways over here. And now, let me show you. Now, let's have a close look right here. See? Now, I'm going to think about undoing the rotation. So, if we're undoing the rotation, then really, this cone now, it's unlocked a secret. That a secret is unlocked in the sense that this cone came out this cone came out as a result of rotating this right triangle. Now the right angle is right here. So in a flat view, if we place our eye to look straight into this triangle right here, then it's going to look as following. It's just a right triangle. So imagine that we have a region being a right triangle at first, and we can put that tip of the cone or that tip of the right triangle right at the origin to make life simple for us, to simplify things down for us a little bit. And we put the tip right at the origin, and here we have that right triangle, 90 degrees angle right here. Then the rotation will happen. Then in that way, see the 90-degree angle here. And so once we make the rotation, we have the cone. Okay, so I try to undo the cone, undo the rotation, and now I complete the rotation again to make it clear that our solid here, the right circular cone, really came out as a result of rotating a region, okay, a bounded region right there. And that region was, according to the picture we saw, it's a right triangle. All right, so now allow me to put that picture as a hand sketch on the board here. All right, so according to that hand sketch version, then once we realize that this cone came out as a result of a rotation of a region right here, then that region, I got clear with anyone viewing this video that it's a right triangle right here. Okay, and then there's the tip of that, or the vertex of that right triangle is, for simplicity, we put it right at the origin 0, 0. Okay, so in that way, now let's extract our information. So in that way, now if we are incorporating this picture, this region, into our actual cone, then we're going to combine that with the property we already knew about the cone right here. The cone, our right circular cone, has a base radius 2. So now if we undo the rotation, if we flat out the rotation, then this is the triangle, this is the triangle. So in that triangle, in this version of that triangle right here, then the base radius really is this height right here. And that height now is 2. Okay? And then the height of the cone was given in the problem to be 6. And so now in this undo version, this version of the region before rotation that generated, before the rotation that generated the cone here, then the height really was this other longer side of our right triangle that we are currently sitting at right here, with the tip or with the vertex right at the origin. Okay, so 6 is this edge right here. All right, so now in the way how I'm setting my triangle, my region right there, in a way how I'm seating it, then it looks like, and at the end allow me to save this to the end to discuss further, but right now I can tell a little bit that it's actually our choice. We can make our choice to seat the triangle this way, to align the rotation with the x-axis. That's what I'm trying to say. And so at the end I'm going to be able to explain a little more. Okay, but right now seating the triangle to be consistent with the rotation around the x-axis here is just a choice of mine right here. Okay, so now we're going to treat the x-axis as the rotation axis. Okay, so now in that way, clearly speaking, once we imagine again and back on that picture on the computer screen, all right, and so once we are rotating it, once we start rotating it, okay, then we are going to have disk, okay, because we are going to have so many stripes here along the way from the beginning to the end. Okay, so now at this point right here, we have seen through quite a few examples that I offer in a general lecture right here. So this shaded area right here, now when we're rotating it, then we can the stripe that we're drawing, the stripes here are going to be from where the center of rotation or the rotation axis here, from where the rotation axis here, we can draw the stripes that reach out to the upper limits or the other boundary of the region right here. Okay, and once we are rotating, then each stripe is creating for us a disk. So right here, for example, right at the beginning right here, right at the beginning or right at this ending part of the region, we already have a stripe right here. The ending stripe is this vertical stripe, perpendicular with the x-axis. And now as we're rotating it, we have a disk right in front of us. And again, just like how I explained throughout the examples or throughout the work that I gave in the general discussion lecture, then we need to put our eyes to align with this x-axis, with this rotation axis in general. So what we are facing right now is a circular disk right in front of us. Okay, and so now again in that way, on this hand sketch right here, I am placing my eyes here, looking straight at it. So each stripe is supposed to be perpendicular with the rotation axis. That's the way how we're going with disk methods. And so when we're rotating it, as you have seen enough throughout the demonstration with Desmos, then each stripe here is going to give me a disk, because that stripe once rotated, it's going to be giving me a disk. And that's how we will end up with that cone right there. Okay, and so now by looking at this disk right here, then each disk itself right here, see, so now I'm going to extract out one disk. The rotation axis comes out like that, right? And each disk here that's the radius, because that's the stripe right there. So it looks like now that is going to be the curve of our function. We're going to be having that curve, okay, and then the stripe comes out from the rotation axis out and stops at the curve like that. Okay, and so now each disk, again, just like the examples I pointed out in the general discussion lecture right here, then each disk has a thickness. Okay, it has some thickness right here. All right, so now after sketching down all that information and kind of make some planning, then here we are again. I am again going to remind anyone, the whole idea of doing this problem and eventually using an integral, I have to remind an integral is accumulation. Okay, a definite integral is accumulation. So now applying that concept, a definite integral being accumulation, applying that concept into this work, finding a volume right here, then the idea now is that each of our disk here, each of our circular disk here is regarded as generally as a cross section. And each cross section here has an area. And once the area is multiplied with thickness, we end up with a little volume of a thin disk. And so now here's the idea. Again, just like how I have delivered in the general lecture, what we need here fundamentally is to find the cross-section area. And once we found a cross-section area, we are going to multiply, take the product with the thickness. All right, it's the thickness. And now that gives us the volume for one infinitesimally thin disk. And now we're going to be accumulating all of those disk volumes from a start, okay, to the end, to an end right there. And that's how we will obtain the exact volume of our cone right here. And so you can see that each disk at different instance of x, each disk has a cross-section area being big or small depending on where we're at. Okay, on this x-axis, depending where our stripe is at on the x-axis here. Okay, and so now in that way, let's look at that a little more closely right here. So as I had to erase that because I need to make some space right here. But so step one in my advice, that which came out as my own personal experience, and I discussed this in the general lecture again, that I found it personally easier to first start out by finding the thickness of each of our disks right here. So again, with a quick graphical description, the disk is standing like that, where it's perpendicular with the x-axis. Okay, because the x-axis now is going to be our rotation axis, so the thickness here is like that. So it makes sense now that the thickness, according to the way how the picture is, it's going to be the infinitesimally small change in x value. So now in formal calculus term, it's a differential dx. All right, so in that way now I'm clear. It's just the way how we place. So we made a choice to put our cones to align with the x-axis, to assume the x-axis, to use, we align our cone to assume the x-axis as the rotation axis. Okay, and so consequently, in that way, then we realize that our thickness in this case is the differential dx. Okay, and so now just like any of the example I gave in the general lecture, then I am going to immediately, once we found and recognized dx right here as the thickness, we're going to immediately revise our fundamental about the accumulation here. So the accumulation here is still going from accumulating from a start to an end. We're still going to have to find out our cross-section area. Okay, and right now we haven't, but then at least we knew now, we have found out now that our thickness is dx. So each cross-section area needs to multiply with the thickness being dx. Okay, and so now once we have arrived upon realizing our thickness here needs to be a dx, then now it gives us a clear plan for the next step. So the cross-section area here as a function, we need to recognize that cross-section area as a function of x, because the d expression here is a dx. Okay, and so now it's time to look for the area of the cross section, or I call that cross section area. All right, so let's find out what that can be. And so now again, back in the picture, each cross section came out by rotating the stripe, but the stripe here has height where it comes out from. So rule of thumb is always it comes out from the center of rotation, or the rotation axis, and comes out and hits to that other boundary, to that boundary where it stops like that. Okay, so the boundary here really is, so it's a graph. It's a graph, and so we need to now find out. Originally it's just a geometric figure, But now with that line here, once we put it on the x-axis, once we put it on the x and y graphing system right here, then there's a way to find out. First of all, we realize it's a line. It's a line, it's a straight line. So we realize that we can express that line here based on its given information. We can express that line as a function of x, because now at each different x value, then we have a different height output here. So we can treat this curve here as a function depending on the x value. If x is here, then that stripe get a higher output right here. If x is here, then that stripe here has a lower output, a lower height right there. Okay, and so in that way, let's find out a little bit. Let's do some scratch work right here. I'm going to quickly swing over to this side of my board. Okay, so there we go. We have a line that going, and see, even having that vertex right at the origin was a choice, but that choice made life simpler for us. Okay, and so once again, in this setting right here, we have a triangle, right angle right here, but basically I'm seeing this as a line. There's no need to extend that line infinite, but any line now has a slope. Any line has a slope, and so perfect. That right triangle setting right here is the perfect information for us to find our slope of this line. Clearly speaking, in the way how we are currently seating our region here, then this line is having a positive slope. So slope is for this line is simply just that rise over run that we know from algebra. So now let's apply some algebra into this work right here. This rise is simply just our base radius, because once we're rotating that, this height right here is going to become our base radius of the cone. Overrun, this run here is that height 6 given with the cone right here, given as part of the description of the cone. And so now all of a sudden we feel like our line here is supposed to be y equals mx plus b, or f of x equals mx plus b. We purposely want to express that as a function of x. And now we found slope is a rise over run. So rise 2 over 6 runs. So now it's going to be a, okay, so slope is found to be 2 over 6. Quick scratch work right there, and that is going to be a 1/3. So now I know that y equals 1/3 x plus b value. And then now like I said earlier, it's a choice, it's a decision that we put that vertex here right at the origin. It's keeping life simple for us. So how is that so useful in this case right here? Keeping that vertex at the origin, that means this line here does go through right through the origin. That means, or in other words, 0, 0 is 1 point on this line. Okay. What if we put that triangle at some other place? Sure, that worked too, but it's gonna take some more time to figure things out. But if we can also put the triangle, the region somewhere, not at the origin and still on the x-axis maybe. Okay, but the line is going to look like this, so we're going to have to spend a little more time to figure out where that point is. Okay, but now that's not the case we're doing, because we obviously didn't decide to go that way. Okay, and I decided to put that origin, to put that tip, the vertex of the cone here right at the origin. It's all about making life easier for us. Okay, and so in that way, I'm going to substitute 0, 0 into this equation for 0 for x, 0 for y, and we're solving for b right here. So in that way, it looks like b really is, okay, so 0 equals 1/3 times 0 plus b. So truly, b equals 0. So now we complete our equation. Our equation of this line here. So this hypotenuse of the triangle is really having, if we're putting that with the coordinate axis systems, then it's the graph 1/3 x right here, or it's the graph of the function 1/3 x. So this is our function now in terms of x. We have expressed any of our height. So when x is here or when x is there, this x here is a 1/3 times x. This height right here is a 1/3 times x, depending on wherever x is, between anywhere from that value here to ending here. Okay, and the reason I'm going a little bit abstract about from here to here, because I want to go back and give a clear explanation later on and point out that we can also think about, if you are a student doing this completely on your own, there's a way to reveal for us where we go from start to end of our region here. Okay, but now on my other board, so the cross section, each stripe here is found by that function 1/3 x. And so now here's the thing, area of any, again, area of any circular disk or any circle is always pi or square. And now clearly the height here is the radius, the height here from the rotation axis out to the boundary of the region is the function's height, the function outputs, or the height, physical height right here. So that means now I'm looking at area equals pi times, and r here is that 1/3 x, and now I'm going to have r squared. All right, so now clearly this is a function. The area of each disk, each cross section is a function in terms of x. So now I am going to fill this into my accumulation formula right here. So with this fundamental that I'm currently revising, then the cross section area now is found by, in parentheses, pi times, in parentheses, 1/3 x r squared. So that's cross section area multiplied with that. Okay, so all that here. All right, so now let's one more time look back at the picture. If we are accumulating, and I explained this in the general discussion lecture right here, anytime that we're placing our solid to align with the x-axis, okay, and anytime that we place our rotation to align with the x-axis and taking the x-axis as, or taking any axis that's parallel to the x-axis here as the rotation center, as the rotation axis, then the start would be on the left and ending going to be on the right. So start and end, start on the left and ending on the right. Okay, so now that means now if we're looking closely at this picture, or maybe the other version of on my other board is slightly better. So we're accumulating all of these discs right here. Each stripe gives us a disc. So accumulating all of these discs. So it looks like we're going from 0. It makes sense to go from 0 at the start. It's ending at wherever that it completes the height of our cone right there. So our cone here, again, this is just a projection of that cone right here, but now this length right here I explained earlier, this is just the height of our cone right here. So it goes from 0 to 6 here. It makes sense that way. Okay, and so now in this way, here we are at that step where we completely nail down our integral. So this is from 0 to 6, okay, and that is, ladies and gentlemen, it's the volume formula. It's completing this integral, this definite integral will give us the exact volume of our circular cone right there. Okay, and so now allow me to erase this extra work right here, okay, because we've had it there long enough. Now I'm going to need the space to complete out this. So fundamental theorem of calculus now, and that's why I said earlier that it is strictly required that you working on this video lesson, you learning from this video lesson after you have already learned about what the fundamental theorem of calculus is. Okay, and so now, again, fundamental theorem of calculus says we can take the antiderivative of this. And by the way, let's revise this overall the integral a little bit to make it easier to work with. So pi is a constant coefficient. Now 1/3 x is all inside of the square, so algebraically it's going to be 1/9 x squared. Okay, so I can pull out this integral right here. I can pull out, it's going to be 1/9 times pi, so it's pi over 9 right here. And integral, the accumulation multiplied with accumulation from 0 to 6. But our function now is simply just the x squared function. And now you can see how easy we have, how simplified we have brought our integral down. Okay, so that's once we complete this integral with the fundamental theorem of calculus, the answer there that we come out with this is the volume, the precise volume of this cone right here. All right, and so now it's pi over 9 times all that. So here I'm going to go finding the antiderivative. So pi over 9 times 1/3 x cubed 1/3 x cubed, and I need to substitute this. I need to evaluate this antiderivative according to the fundamental theorem of calculus from 0 to 6, lower end to the upper end of our integral. All right, and so now this antiderivative is entirely independent on x right here, and it's multiplied with x cubed. So think about once we are substituting values in, we have pi over 9 times, and by the way, pi over 9 times 1/3, I can make that as a pi over 27. Okay, pi over 27. All right, and so now I'm going to multiply that with 6 cubed, because this is where I'm substituting x equals 6 into my antiderivative. And so x cubed, now with 6 substituted in, it's 6 cubed. I'm subtracting, but hey, wait a minute, all of these terms, the entire antiderivative here, once we substituted x equals 0 in here, your math is mature enough to see this. It's going to be just simply a 0 out. So save me some from some, the spending time writing down too many steps, little steps like that. So the whole thing here, once substituted x equals 0 in there, it's just a 0 out. So now all you have now is, and I don't even need any advanced calculator. All we do now is just complete out that final calculation. Okay, and so that is how I have. Okay, so the 20s, all of that together will equal. Okay, long story short, all of that together, the will equals all together 8 pi, okay, as our final answer. All right, and so now again, just like how I explained in the general discussion lecture, we have to double check to make sure our answer here makes sense with what we're being asked to do. We need to find a volume. We need to find a volume. And so after successfully completing our work on the integral here, the answer came out being a positive, which makes sense with being the nature of this problem being finding volume, because volume will always be a positive quantity. It makes no sense to have a negative quantity, and it's not fun at all to have a volume that's being 0. Okay, and the reason I mention this again, because many times when we're only simply doing an integral work, then our answer for an integral, for a definite integral work, can be a negative, because integral can be applied in so many different places. But here, when we specifically apply definite integral into finding a volume, we need that final answer to be a positive. So here we go, the answer was positive. Okay, so we're good to go with that. All right, and so that's how we applied our understanding. And so this problem is a little more advanced than the usual kind of example problem where we can see a straightforward direct application of the disk method right here. It's more advanced in the sense that we have to realize that the solid we have here really came from rotating a region like that. Okay, but now let me talk a little further about that. The whole reason I brought up this example is that I want whoever viewing this video, whoever is learning from this video, is to realize how many solids out there actually come out from rotating a region. Okay, so let me bring out a few examples, and from there, after this particular problem that you can do, you can apply your understanding into finding your own solid out there that it came out from rotating a curve around a region right here. Around an axis. So now let me erase this board here. So yes, the problem we just did now is a cone. So cone came out. All right, so cone came out by rotating a right triangle like that and rotating that around. And if we put one side here, we put one longer side or shorter side of our right triangle along an axis of rotation, then we will create the cone. Okay, and so in case if we are rotating around a horizontal axis, then we're going to have the cone sitting sideways. If we're putting our right triangle standing straight up, okay, and rotating around a vertical axis, then we're going to have a cone like this, standing up. Okay, but that's in the end it's a cone. It came out from rotating a region. Okay, so we have that picture. We nailed that down, and it came just right out from our problem. So earlier I said putting it sideways is just a choice, because yes, you can also think about the same triangle there. It can stand straight up, and then we're rotating that around the y-axis. That problem can be done as well. Okay, it's just here I chose to go with the sideways, so we work with the more friendly x variable. Okay, but so outside of the cone, what else? What other solids really came out from came out as a result of rotating a region? Okay, cylinder, very common shape in our daily life. A pipe shape or a cylinder. Okay, cylinder. You can imagine that we put that rotation axis right through the center of the cross section right here. All right, and so what kind of shape, what kind of regions that's after rotating give us a cylinder? Any rectangular shape. And now we can put that align with the x-axis and start rotating. There we have for ourselves, we created for ourselves a cylinder. Okay, or the same rectangular shape, we can put it standing up and rotating it around the vertical axis. Then we have a cylinder that is standing straight up, but that is a cylinder. So cylinder, again I emphasize, cylinder came out from rotating a region. The region is here, and we look at those stripes, and once we're rotating those stripes, it gives us discs. All right, what else is another known very common solid out there that came out as a result of rotating a region? Sphere. A sphere, any sphere. Okay, like those balls that we play as a soccer, those balls that we play as a tennis ball, those balls that we play as a basketball, they're all the shapes of a sphere right there. Okay, so what do I see in a sphere? A sphere comes out from rotating a half semicircle region. A semicircular region right there. There's your semicircular region. And once we're rotating it around an axis, okay, and really vertical axis or horizontal axis like this should not matter, but once we're rotating it, we have a sphere. The stripe here gives us the sphere. I mean, the stripe here gives us the disc of the cross section. Okay, or we can think about a semicircular region that's standing vertical like that, and the stripes are going here, and we're assuming that we using the vertical y-axis for the rotation axis. So once we're rotating it, okay, this region right here as a semicircular region, once we're rotating it, we are ending up with a sphere again. Okay, and that's where spheres, any spheres come from. Okay, and so now outside of these a very common shape that already have a formula. Outside of these common shapes right here, what are the shapes out there that came out from a rotation? Okay, so a bottle. Could be a wine bottle or just whatever bottle, water bottle. A water bottle or just any kind of bottle right here. Okay, so I can see this as, if we can find out what that curve is, what that function is, having a curve like this, then together with the x-axis, for example, it creates a region like that, and now we're going to be rotating that region. We end up with a bottle. Okay, bottleneck is here, and there's our bottle. And of course, forgive me that I'm not the best artist out there. I'm not the best drawer out there that can draw the nice picture, but that you will see what I mean by doing that. So we just simply rotating a region that's created by a bent curve, a nice wavy curve like this, and rotating it around, we get a bottle. There are many shapes out there that come out from rotating a bottle like that. So be ready. So because there are no instructor that can cover all kinds of examples out there. So I point out this generality right out from this, right at the end of this example, so that you can realize that, and you be aware that there will be problems out there where people will ask you to calculate the volume of a very common shape. Gosh, you see these shapes every day. But now if we use calculus and specifically the disk method right here, how are we going to find that? So that generality was brought up in the problem that we worked through the cone right here. See, so we got to kind of imagine that, roll back to before we rotating it. What region was that? Okay, and once we rotating it, and when we sort of unrotate that, when we kind of rolling back to that point before we rotating the region, then we have to also decide, should we place that region along the x-axis for rotation or along the y-axis for rotation. It's all about you making your own decision to make life simpler for you, to make the calculation go simpler for you. Okay, and once you've had that region successfully identified, then we're gonna start finding out what curve defines this shape right here. What curves define that boundary? It could be a nicer semicircle. Okay, and at this point, anyone learning calculus knows the equation. And you also have your choice for simplicity. In case it's a circle, you can put it right at the origin. Okay, and then anyone learning about calculus should know the equation immediately on top of your mind for what the equation expression for a circle. Okay, and then more advanced than that, and cylinder is a flat rectangular cylinder is way too easy actually. And then outside of that, see, like that bottle I brought up earlier, then we need to maybe come up with some function that has a shape like that, maybe like a cube function or something, or cubic function. Then that will give us a shape like that, and it will come out with a bottle for us. Okay, all right, and so that's hopefully one example I brought up. Okay, but it gives a generalization about gives an opening door for many other problems where we can successfully find volumes of these from elementary common volumes to more challenging, complicated one. But a lot of them came out from rotating a region, okay, to obtain a volume. And the solid here came out, it's a solid generated by rotating a region. Okay.